Thank you very much, and good afternoon, ladies and gentlemen. As previously said, my name is Vicente Moret, and I am a professor at the University of La Coruña, and I am involved in several research projects, some of them related to the field of quantum computing. Before starting with my talk, I would like to thank Fundación Barrié and Coruña Innovate Summit for giving me the opportunity of presenting the European project Next Applications of Quantum Computing. I also would like to thank all the audience for their assistance, and I will make extensive this gratitude to all the students and colleagues that did consider that spending part of their time talking about quantum computing is not such a bad thing. Finally, but not less important, I want to congratulate Dr. Neasqc for his extremely relevant work in quantum computing and for having received just yesterday the degree of Doctor Honoris Causa for the University of La Coruña. I have organized my presentation in 3 parts. In the first one, I will go through some very basic principles of quantum mechanics in order to define a simple framework for further discussion about quantum computing. In the second part of my presentation, I will explore the history of quantum computing, as well as the current situation of quantum computing in the world, in Europe, in Spain, and in Galicia. Some economical information will be included in this part of my speech. And finally, in the last part of my talk, I will present the Next Applications of Quantum Computing European project, a project whose purpose is the application of quantum technologies for solving practical and industrial problems. First of all, I think you should know that my background in quantum computing is not spectacular. In fact, I come from the world of theoretical chemistry. Then life draws me to the field of artificial intelligence. But when I was a student at the University of Santiago de Compostela, I had an excellent professor in quantum chemistry, Dr. Julio Casado Linarejos, who initiated me into the wonderful world of quantum mechanics. Several years later, when I thought that I did forget all about quantum mechanics, I read a paper on quantum computing, and believe it or not, I understood it. And this is the reason why I started again with my old interest in the quantum field. Let me now say to you that I am an academic person, and as all the academicians do, my major interest is asking myself questions. And the first question I have to ask to myself, and also to ask to all the audience, is the following question. Why quantum computing? Let me concentrate in this plot. This is not exactly Moore's law, but it is something similar. The basic idea is that as time evolves, our computing devices are faster. But this increase in the speed of the calculations is mainly due to the decrease of the size of the computing devices. If we observe the graph, we can easily identify that we are working with computing devices whose dimensions are of just a few nanometers. And with this size, quantum behavior has to be taken into account. In fact, the design of new computers that take into account the restrictions of quantum mechanics is already a must, not an alternative. But despite that quantum mechanics usually goes far beyond of our intuition, we find practical applications of quantum computing and quantum mechanics everywhere. Let me tell you a brief story. When Paul Dirac was trying to unify the relativity of Einstein with the Schrödinger ondulatory mechanics, and assuming that physics is physics independently of the size of the system we are dealing with, Paul Dirac had to include a term in the Schrödinger equation that defined a particle with the mass of an electron but positively charged, and he called that particle positron. Nobody believed in such a strange particle, but few years later an experimental physicist named Anderson detected this particle. Now positrons are in the central part sorry, of some medical devices for diagnosis, in the way of positron emission tomography, also known as PET. The first thing to think about is that something born inside abstract physics has now a practical application. The conclusion is yours. But as I said before, the world of quantum, although it escapes from our intuition, is already here. There are however, some phenomena that are difficult to understand, not to say impossible to be understood. Among these strange behaviors, we can mention the indeterminacy principle, the superposition of states, the tunnel effect, or the duality wave particle. I will give you a brief overview of some of these phenomena, just before telling you a surprising phrase of the great, brilliant, and original scientist named Richard Phillips Feynman. Let me start with the tunnel effect. Assume we have a classical particle that is moving with a given kinetic energy. There is a wall that can be interpreted as a potential barrier, and if the kinetic energy of the particle is less than the potential energy of the wall, the particle hits the wall and then rebounds. The particle is not capable of trespassing the wall. That is in the macroscopic. But imagine that we are in the quantum world. In this case, unless the wall is infinitely high, there is a probability that the quantum particle trespasses the wall. Let me illustrate the situation with an example. Imagine that we have a very nice nephew and we want to take him to the zoo. In this case, we will choose a macroscopic zoo, since we can be sure that the tiger will not be able to get out of the pit. On the other hand, let us assume that our nephew is repellent and rude. In this case, we will choose a quantum zoo, since there is a probability that the tiger get out of the pit and eat our nephew. The problem now is who explains it later to our brother-in-law, but this is another problem. In any case, listen, the same thing goes for information. When we work at the nanoscale, information leaks through quantum slits. Let me now explain something about the duality wave particle in the subatomic world. When I was in the school, I learned that an electron is at the same time a wave and a particle. But today, I'm not sure this is true. Imagine that the cylinder in the figure is an electron, but a cylinder is a cylinder, and therefore an electron is an electron. The problem is that we live in the macroscopic, and the electron is a subatomic entity. For this reason, we cannot have an idea about what a real electron looks like. However, we can understand some properties of the electron by using imagination. Let me illuminate the cylinder from the lower right part of the figure to obtain a projection on the wall. This projection is a rectangle, so I can conclude that a cylinder is a rectangle. But now I will illuminate the cylinder from the lower part, left part of the figure, and the projection I have on the yellow wall is a circle. Then I have to conclude that a cylinder is also a circle. The conclusion is that a cylinder is both a rectangle and a circle, which is not true. A cylinder is always a cylinder, but we identify different properties depending on the way we look at it. And the very same thing occurs with electrons. And now I will go back to the strange nature of the quantum world, and for this I will use the words of Richard Feynman, who in his famous conference at Cornell said the following: "Nobody understands quantum mechanics. No, you are not going to be able to understand it. You see, my physics students don't understand it either, and that is because I don't understand it. Nobody does. The theory of quantum electrodynamics describes nature as absurd from the point of view of common sense, and it agrees fully with experiment. So I hope you can accept nature as she is, absurd." It is obvious that if Richard Feynman declares that he did not understand the nature of quantum mechanics, we should think about our own understanding of such a difficult stuff. To continue with my talk, I will now present a funny way for representing bits and quantum bits. This way of focusing the problem will lead us directly to the notation of Dirac and Heisenberg, which in turn is in the core of the axiomatic formulation of quantum mechanics. The state of a bit can be 0 or 1. A bit can be considered as a measure of information that is related in logical terms with a given statement. Thus, a 0 bit indicates that the associated statement is false. Conversely, a 1 bit indicates that the associated statement is true. But in order to perform calculations with bits, we need a physical device. For example, a circuit with a light bulb. When the circuit is off, the light bulb is sad and the statement is false. This is represented as a 0 bit. But listen, if the statement is true, the circuit is on, the light bulb is happy, and this is represented by a bit 1. But let us take a look to the marks A and B located just before and after the light bulb. Notice that when the circuit is off, E equals 0, the light bulb is sad and B equals 0. But if the circuit is on, then A equals 1, the light bulb is happy and B equals 1. That means that A is always equal to B, and the corresponding values depend on the state of the circuit. A equals B equals 0 if the circuit is on, A equals B equals 1 if the circuit is on. Let me now put these arguments in the tabular form. We can build a table with two columns representing the two possible states of A, that is A equals 0 or A equals 1, and two files representing the two possible states of B, that is B equals 0 or B equals 1. As the circuit works as a whole, it happens that if we go from A to B, we have the column matrix AB with the following values. Circuit off implies A equals 0 and B equals 0 is true. and A equals 0 and B equals 1 is false. The same argument applies when the circuit is on. That is, A equals 1 and B equals 0 is false, and A equals 1 and B equals 1 is true. This column representation is the Ket notation proposed by Paul Dirac. But if we go now from B to A, then we have the same result but in the form of a file matrix, and this is the Brown notation proposed by Paul Dirac. As you can see, nothing especially difficult. I'm going to finish the first part of my speech by talking a little bit about the problem of measuring quantum bits. Again, I will try to clarify some imprecisions that we learn at the school. There we are usually told that an electron can reach simultaneously two holes of one quantum American billiard table. But I'm not sure on this. Assume the following experiment. We have two walls. The first wall as a hole, and the second wall has two holes. Between the two walls we have something capable of attracting particles 0 or particles 1. And according to what we have been told at the school, the particle can pass simultaneously through both holes. Let me explain why. If the particle is a 0, then after collapsing to a bit 0, due to Heisenberg's principle of indeterminacy, the particle will go through the hole 0 of the second wall. And the same thing happens if we have a pure 1. The collapsed bit will pass through the hole of 1 bit of the hole 1 of the second wall. But usually electrons or qubits are in superposition. That is to say that they are simultaneously in both situations, 0 and 1. But, and this is a must, with a certain amplitude of both situations. Then the particle will go through 0 or through 1 with a given probability, which is related with the corresponding amplitudes of Ket 0 and Ket 1. Once I did finish with the academic part of my intervention, I will now explore both the past and the recent history of quantum computing. And I will talk about the history itself, but also about the economical implications that are currently associated with the advent of quantum computing. And the first question is, what can we do with quantum computing? Or the very same question, what can we do with quantum computers? It seems that everyone agrees on that examples. Quantum computing could be a way for solving problems that classical computing cannot solve. Quantum computing paves the way for faster computations in simulations, and for example in the financial domain, quantum computing will permit us in seconds the evaluation of the risk of one client. Some 35 years ago, Richard Feynman suggested that if we want to simulate physical systems, we have to take into account the laws of quantum mechanics in our computers. Moreover, he anticipated that not later than 2050, we would have quantum computers. Apart from the fact that, as usual, the ideas of Feynman were correct, what nobody could imagine is that just today, people is frequently speaking about quantum computing. And moreover, quantum computing is now so important that almost all countries are making great investments in the field, especially in the United States and China. Definitely, we are in a quantum race in which companies and governments are engaged. Although the first efforts were made by universities and research centers, very soon big companies as for example IBM, Alibaba, Google or the Canadian D-Wave understood the great potential of quantum technologies. In this context, in 2016, IBM announced his first quantum computer with 5 qubits. 12 months later, said company presented a new quantum computer with 16 qubits, which was followed by 6 months later by a new quantum system with 20 quantum bits. And in 2018, IBM presented a general-purpose quantum computer with 50 quantum bits. And the initiative was immediately followed by Google. This big company started to talk about the quantum supremacy and presented a quantum system with 54 quantum bits. I will now to explore the situation of quantum computing in some countries. In the United States of America, there is a quantum program involving $1,200 million in the development of quantum technologies over the next decade. And a significant part of this investment will be dedicated to 5 research centers, and also companies and universities will benefit from this program. If we talk now about China, in 2017 the government of China announced the construction of a $10,000 million laboratory for work in quantum computing. Also, Alibaba is working on a 100 qubits general-purpose quantum computer expected to be launched by 2030. In this context, and according with research and markets, this year near 8 million euros will be allocated to quantum computing technologies. In 2026, the figure will rise to more than 26 million euros. Also, around 7% of large companies worldwide already dedicate at least 17% of their annual technology budget to the quantum game, and this percentage will reach 19% by 2023. That means tomorrow. Another interesting thing we should talk about concerns the role that Europe and Spain play in the quantum race. According with Dr. Ignacio Cirac, quantum computing gave us the power to perform much larger calculations. But, and in this context, we have a question. Will Europe be a loser in the quantum race? The answer to this question relies much on the scientific, technological, and economical efforts made by each of the countries in the continent, as well as on the efforts of Europe as a whole. In this respect, we see some activity in Finland, in Sweden, in Denmark, in the United Kingdom, in Germany, in the Netherlands, in France, in Switzerland, in Austria, and in Spain. But the corresponding engagement of these countries in the quantum race is not homogeneous. In fact, in Europe, only Germany can be considered to be in the top of the countries that lead the quantum race. And this is due about the geographical dispersion of the quantum technologies. Europe is in a clearly lower step and with market inequality depending on the country we consider. Despite being the scientific cradle of many of the techniques and premises of quantum technologies, in the old continent we have not been able to materialize this knowledge in developments. in developments likely to reach the market in the medium term, and only the quantum flagship program is seriously concerned in quantum technologies. Next, what about Spain? Only a few projects from the Consejo Superior de Investigaciones Científicas, CSIC, and from Spanish universities managed to stand up to very specific applications of quantum computing. Some examples are cryptography or financial applications. And last, in Galicia, quantum technology developments are almost exclusively done in Neasqc and in the three universities, Santiago de Compostela, working in quantum information and quantum mechanics, the University of Vigo, working in quantum communications and cryptography, and the University of Coruña, working in quantum computing. Also, and this is important, the local government of Galicia is making an important effort in the creation of a quantum ecosystem named the Polo Quántico. I will finish the second part of my talk by saying that in order to fill the gap, when the train passes, we have to get on, even if the train is moving. We have to consider very seriously the financial resources of the different programs, as well as the consolidation of synergies between research entities and companies, because perhaps this is our last opportunity. And I will go finally through the last part of my presentation, the next applications of quantum computing European project. This project is devoted to finding real industrial and then user applications of quantum computing in the Neasqc stage, noisy intermediate scale quantum stage. As I said before, Neasqc is the acronym, and in the noise intermediate scale quantum stage, the leading quantum processors contain at the most few hundred of quantum bits, but these processors are not advanced enough to reach fault tolerance, nor large enough to profit from quantum supremacy. The acronym Neasqc was coined by John Preskill in 2018, and it is used to describe the current state of the art in the fabrication of quantum processors. The term noisy refers to the fact that quantum processors are very sensitive to the environment and may lose their quantum state due to quantum decoherence, and also in the Neasqc stage, the quantum processors are not sophisticated enough to continuously implement quantum error correction. Finally, the term intermediate scale refers to the quantum volumes related to the not so large number of quantum bits and moderate gate fidelity. Next application of quantum computing is a 4-year project starting the 1st September 2020. It is a multidisciplinary consortium of 12 companies and research labs that has been funded by Horizon 2020 program under the complementary call of the Quantum Technology Flagship, and the funds were somewhere around 5 million euros. The companies involved in this project are Atos, AstraZeneca, Neasqc, EDF, HQS, HSBC, iCheck, the University of Leiden, Tilde, Total, the University of La Coruña, and the University of Lorraine. And the main purpose is boosting practical applications of quantum computing in the Neasqc stage. The project deals with 9 Neasqc-compatible use cases, and in the project, industrial and academic partners are working together. Main areas of research and development are chemistry, machine learning and optimization, and symbolic artificial intelligence and graph algorithms. The project brings together academic experts and industrial end users to investigate and develop new quantum-enabled applications. Next applications in quantum computing is use case driven, addressing practical problems, and has the ambition to initiate an active European community around niche quantum computing by providing a common toolset that will attract new industrial users. The consortium has chosen a wide selection of niche-compatible industrial and financial use cases and will develop new quantum software techniques to solve those use cases with a practical quantum advantage. To achieve this, the project brings together an unprecedented multidisciplinary consortium of academic and industry experts in quantum computing, in high-performance computing, in artificial intelligence, or in chemistry. The ultimate ambition of the Neasqc project is to encourage European user communities to investigate new quantum computing. For this purpose, the project consortium will define and make available a complete and common toolset that new industrial actors can use to start their own practical investigation and share their results. Going into the details, the basic objectives is to develop 9 industrial and financial use cases with a practical quantum advantage for Neasqc machines, the building of a strong user community dedicated to industrial Neasqc applications, to develop open source Neasqc programming libraries for industrial use cases with a view to facilitate quantum computing experimentation for new users, and to develop software stacks and benchmarks for the quantum technology flagship hardware platforms. Let me talk now a little bit about the use cases, the basic use cases in the project. As far as symbolic artificial intelligence and graph algorithms is concerned, we are working in quantum probabilistic safety assessment, in quantum natural language processing, and in quantum rule-based systems for breast cancer detection. And the companies involved in this part of the project are Neasqc, EDF, the University of La Coruña, Tilde, Neasqc, and the University of Leiden. The second main area is machine learning and optimization. In this area, we are working in hard optimization problems for smart charging of electric vehicles, in reinforcement learning for inventory management, in financial applications, and in HPC MEC segmentations. And the companies involved in the project are Total Energies, EDF, the University of La Coruña, the University of Leiden, Neasqc, HSBC, and the University of Lorraine. Finally, let me now present our goals in chemistry, which are the following. The goal of this work package is to bridge the gap between the recent proof of concept quantum chemical computation on Neasqc processors and actual industrial scale quantum chemistry problems. To this aim, we will create software tools to integrate classical quantum chemical codes with quantum computing modules, and the companies involved in the project are HQS, Total Energies, AstraZeneca, and Neasqc. And just to conclude, I will show you a collage with pictures of the leaders of the Neasqc project. These persons are trying to get into the train before the train passes. And that's all for my side. Thank you very much for your attention. Thank you.